Slides.
Yes. Okay. So our next speaker, and the last of this season, is Diego Morán Ramirez. He is an assistant professor in the Department of Industrial Systems Engineering at Rensselaer, RPI. He holds a Rensselaer Polytechnic Institute. There we go. He holds a PhD in OR from Georgia Tech, and a mathematical engineering professional degree, and a master in operations management from Universidad de Chile. Prior to RPI, he was an assistant professor at Universidad Adolfo Ibáñez, and also in Virginia Tech. His main research interests are in optimization with a focus on the theory and applications of mixed integer linear and nonlinear programming. Um, he has worked on algorithmic aspects motivated by various applications, including in production planning, logistics, and other business and engineering relevant areas. He received the Informs Optimization Society Student Paper Prize in 2012 and the IBM Faculty Award in 2018. We're happy to have you, Diego.
Thanks a lot for the introduction, and thanks a lot for the invitation. This one of my dreams was to present this seminar series, particularly as the last speaker of the season. So we talk today is ongoing work on parametric polyhedra in MIPs. So let me tell you what I understand as a parametric polyhedra is just a polyhedron, a typical polyhedron that we know, but I parameterize it by changing the data, let's say the matrix or the right-hand side vector.
Diego, sorry to interrupt. Could you, on the bottom of the screen, that black box with the video, just swipe it up to the left or the right?
To the left or the right.
Yeah, like that. Perfect.
Okay, thank you. Okay, so yeah, polyhedron where you change the data. That's a parametric or family of parametric polyhedra, whatever you want to call it. And this data could be taken in an arbitrary set. Typically in this talk, because it's the only thing I know is that I will only change the right-hand side, and this will be taken in a lattice. Think about, b being an integral vector, for instance, as I'm saying here. So this is a parametric polyhedra. So this talk is about properties of families of this parametric polyhedra, and properties in particular for the integral halves and for cutting plane closures. And in this particular part of the talk, I will fix the left-hand side matrix, so I will only change the right-hand side. And this is ongoing work with Silvia Di Gregorio. I will call it future ongoing work. We need to start discussing some other things. So for the second part of the talk, I will present properties of parametric polyhedra that have the same integral half. And this is joint work with Gustavo Angulo. Okay, and here we'll present some formulations for the asymmetric traveling salesman problem. So before going to the talk, I want to talk about a fun fact. This parametric polyhedra, I find out that they also have applications in parallel computing, compilers, and so on. I think they use them for loops. You have a loop here, and this loop can be represented as a polyhedron. And they are interested into parameterize this polyhedron by an integer number. This is all my understanding, but I find it very interesting that they do this. And there are some words related to parametric polyhedra with this application in mind. Okay, so first part, general families of parametric polyhedra. And first, I will start by showing you some properties of the integral half. So here the polyhedron has a fixed matrix. I will change the right-hand side. And first, I will present some definitions. What is the integral half, just in case? Is the convex half of solutions, meaning integer solutions inside the polyhedron. And I will start by showing you some results that are known in the literature. The first one I know is it's called the B half of an integer program. And in particular, this paper presents the following result. So I give you my parametric polyhedron, I compute the integral half, and this integral half can be actually computed with the following formula. So you give the constraints of the polyhedron, and you add this family of constraints. And this family of constraints are independent of the right-hand side. So in order to compute, then you compute the function in the columns of the matrix A, and compute the function in the right-hand side B. And these finite many functions work for any right-hand side B that is in a lattice. So this is a description of the interval just in terms of these functions. And these functions are actually sub-additive functions that are related to duality for interprograms. So in a sense, even for a family of parametric polyhedra, infinite family, we have a finite description of the interval. I mean, I'm not claiming that it's easy to compute these functions, but I mean, it's nice to have it. This is one known result. Second known result, and this is very recent. I mean, I saw this. This is January this year. So Eisenbrand and Rothbos actually found a formula for the interval with this parametrized polyhedra. And the result, main result is as follows. So functions, I can give you matrices and a vector, and these do not depend on the right-hand side. And the idea is that for any right-hand side that you consider, you always find one of these matrices so that the interval can be represented as this polyhedron. And the nice thing is that the dependence on the right-hand side is sort of linear, is affine, okay? So this is very nice. And well, this has some applications that we can find in this paper, just to see how you can use this type of results. And the application is as follows. They apply this to two-stage stochastic interprograms. And the idea is that in stochastic interprograms, you have these constraints, this polyhedron, and notice that this polyhedron has intervariables, y. So x are the first stage variables. So if you fix that first stage variable, then this polyhedron you can actually define it as a parametric family of polyhedra, because you have this constraint is equals to this right-hand side minus this variable that actually define different right-hand sides. So in order to solve this two-stage stochastic program, you can consider this polyhedron that is parameterized by these right-hand sides. And since you have intervariables, you can compute the interval by using the formula from the previous slide. And then at the end, if you find this formula, you can solve these interprograms as parametric interprograms as a parametric LPs. So that's essentially what the result allows you to do. Okay, so there's another result also related to intervals, and this is pseudo periodicity. So Moreno and Linciao Wang, they proved that in the plane, so for two variables, there exists some constants that if your right-hand side is large enough, then the vertices of the interval of this polyhedron and the polyhedron where you perturb the right-hand side a little bit by using these constants, these vertices are in one-to-one correspondence. And this is important because, you know, the extreme rays do not depend on the right-hand side. So having the vertices in one-to-one correspondence is a very nice result. And you can see that for this polyhedron, this is the interval. For the larger polyhedron, this is interval. And you can see that the vertices of the intervals are in one-to-one correspondence. Okay, so very nice result. Okay, so this is related to intervals, known results in the literature. So now let me tell you about one known property of cutting planes. And this is also a recent result. I think this paper is from November last year. So the idea here is that we consider GMI closures, so GMI cuts. So in this context, we consider this polyhedron. And you can relax this polyhedron by applying one rule relaxation. And you keep the intervariables, and you generate GMI cuts. I didn't put the formula because it's very, I mean, it's a beautiful formula, but it's very ugly at the same time. It's very cumbersome from it. So I didn't put it. So the idea is that you can define the closure. So adding all cutting planes, GMI cuts to the polyhedron for any possible relaxation. And a classic result in interprogramming is that, I mean, if I give you just one polyhedron, this GMI closure is a polyhedral set. So you only need finitely many lambdas to define the closure. So not infinite many relaxation, but just a finite many. And Becu, they, Chu, and Xavier, they generalize the result for parametric family of polyhedra in the context of approximating GMI closure using statistical data. Okay, so the result is the following. There's a finite set that works for all your polyhedra, all your right-hand sides. So the GMI closure doesn't matter which right-hand side you use, is defined by this same set of finitely many lambdas. So this is a nice result. I mean, even when you have infinitely many right-hand sides. Okay. So yeah, this is the result I know from the literature regarding cutting planes. Very new result. Okay, so before presenting all results, I forgot to put one reference here. I mean, I know that another group of people is also studying parameterized polyhedra. I know that Alex, Ted Ralphs, and Shannon, they're studying cutting planes. Cutting planes. I mean, it's a more applied work using cutting planes based on parametric polyhedra. I wanted to put the reference, but I forgot. So I apologize for that. I am too old, so I don't remember things. So all results. Let me before presenting some results. I mean, I will present an easy case for intuition. So let's say that your family of polyhedra is of this form. So every polyhedron in your family is actually a polyhedron with a fixed right-hand side, and you perturb it by an integer point. And this could be an infinite family. So let's see what happens in this case. Okay. So I mean, what I claim is that we can generalize some of those results for any reasonable closure and interval. And to understand, I mean, why this case is easy, let's look at the interval. So the interval is finally generated in the sense that to compute the interval of this generic parameterized polyhedra, you only need to compute the interval of this fixed right-hand side, and then you perturb this by an integer. And why is this true? Because, I mean, the convex hull of P, P of B inter Cn is the convex hull of P of B plus P of B T, let's say, plus this set P inter Cn. And actually you can forget about, I mean, you can move the interpoint set B out of the intersection because Cn is integer. So this is the convex hull of P of Bt inter Cn plus this interpoint set B, and the convex hull can be applied to the sum. So you obtain actually convex hull of P of Bt inter Cn, so the interhull of this fixed polyhedra plus this interpoint. So, I mean, applying the formula to this, I mean, particular family of polyhedra is very easy. I mean, and you obtain this result. So, and this is telling you that for this infinite family, the interhull, in a sense, is finally described. The only thing that you do is that you perturb by the interpoint. There. Okay, so okay, I'm not claiming that this is the most general result, but it works. So what happened in the case of closures? So I will show you for two closures, split cuts and lattice cuts. So split set is a set of this form, so two parallel hyperplanes, and you add cuts by removing this set from your polyhedron. And this is a typical or generic split set. So this is what you consider for a split cut. Now you also have lattice cuts, where instead of considering just one single split set, you consider a lattice that is defined by this, and a lattice in this case looks like this. You consider all these fibers, these hyperplanes, all of them. I intersect your polyhedra with them, and then you add cuts. For instance, these cuts or this other cut. So in a sense, you compute the integral of these mixed interlats. Okay, so these are lattice or one-dimensional lattice cuts. Okay, so these are closures of cutting planes that have been studied in the literature. So let me show you what can we say for this easy case. So I claim that these closures for split, let's say, are finitely generated because if I want to compute the split closure, so adding all split cuts to the polyhedron, this is the same as, okay, for any split set, I convexify this polyhedron minus the split. I then remember that this polyhedron is this plus the interpoint. And as before, I can take the interpoint out. So I have this expression. And now here, I'm only looking at this polyhedron, which is fixed, minus a split, because you can translate the split, so it's the same. So by known results, for this particular polyhedron BT, this is a finite set of splits that generate the closure. So you go from infinite many to finite. And now you can go back by using the reverse operation. You can go back, you put the interpoint inside again. And then in order to do that, you need to sort of translate the splits as well. So the split closure of this genetic polyhedra is generated by finitely many splits that depend on this fixed polyhedra VT and the perturbation, interperturbation. So, conclusion, I mean, since for my finite infinite family of polyhedra, they depend on this perturbation, then the split closure is only finite up to translation. So let me show you this in a picture. So, I mean, you don't need to look at the formula, but these are the polyhedra I draw here. So it has this red polyhedra, this translated by an interpoint, a green polyhedra, and this also translation, this blue polyhedra. And I want to compute, this is the family, and you can consider that this is infinite family, so you can go even up higher. So for the red polyhedra, the split closure, you can prove that this is defined by this split. Okay, and this split gives you the split closure for the red polyhedra, and for this green polyhedra, the split closure is given by this split, this green split, and for the blue polyhedra, the split closure is given by this blue split. Okay, so for every polyhedra, you cannot use the same split set, but you just translate it. So this red split you translate it to be the green split, and you translate it to be the blue split. Okay, so the split closure of this family is essentially given by this family of splits. So, and this split translated by whatever the interpoint you are using to create your polyhedron. Okay. So, okay, this is what is true for splits. For these one-dimensional lattices, so you can do the same procedure as before, but notice here that we don't have the lattice translated before we have the split translated by this interpoint. And the reason is that for lattices, when you translate lattices, I mean, you remain the same lattice because you're translated by the interpoint. So, I mean, to go back here, if I had this lattice and I move it, I just move it and it's remained the same lattice. Okay, so in this case, the closure of this family, this is a family, is truly finitely defined because it is a finite set that doesn't depend on the translation that they use. Okay, so very nice. And in this case, this is the figure. I mean, the lattice that gives me all these lattice closures for the red polyhedra, uh, for the green polyhedra, and from the blue polyhedra is this lattice, okay, which is defined by this. Do not depend on the perturbation set, okay. So good. So I mean, this is for the easy case, and our result is that for any parametric polyhedra, not necessarily the easy case now, actually for the split closure, there's a finite set of splits and finite many interpoints, so that the split closure of this parametric family depend on this finite many polyhedra and these translations. Okay. This is the result. Yeah, actually, I mean, I think it's a typo. This is not finally many, but because I mean, you can have the infinite family, so infinite translation. Yeah, it's a typo. And the conjecture is that you can do the same also for any parametric family. Okay. For any parametric family, for the lattice closure, you have the same result. But now you don't care about translations, so it's truly finally defined. And it's a conjecture because I only have a partial proof. In a sense, these results follow from the GMI result, but we want or have different proofs. And actually, this GMI result is for equality, constraint polyhedra, and some results in the programming are different from equality, constraint polyhedra, or less or equal polyhedra. So it may need some work still. Okay. Extensions that will work with Sylvia or the summer is, I mean, extend these results to other closures. Instead of just finite of the closure, they are sort of dominance results. So instead of just the closure being finite, what happens is that for every split, this split from a finite set that dominates all the cuts. So the split dominates this split. And I don't know if it is true for this parametric family or not. I mean, for a single polyhedra, it's true. I mean, who knows about parametric families? This is another interesting question. Okay, let me go to the second part, since I only have like 7 minutes. What happens if you consider polyhedra with the same interval? So first, some results from the literature. This is not by me. I mean, this is rank of cut-and-play procedures. So for a split closure, for instance, the rank is you apply the split closure this many times, okay? And it is proven that you can obtain interval by applying it a finite many times. And this defines the rank of the cutting plane procedure, in this case split closures for a rational polyhedra, is the minimum number of times that you need to apply in order to obtain the interval of the polyhedra cube. So there are results called related to reverse rank by Conforti, Del Pia, De Suma, Faenza, and Grab. And the idea is that instead of just considering one polyhedron, consider all polyhedron that has the same interval than a given set of interpoints. So look for what is the worst case rank for all these polyhedra. I mean, I forgot a max here. What is the worst case? And in these papers, they show, I mean, when this is finite or infinite, and whenever it's finite, they give upper bounds in this rank. So they also consider families of polyhedra that have the same interval. Okay, finally, parametric formations for asymmetric traveling problem. This is work with Gustavo Angulo. And the idea here is that, okay, this is the asymmetric TSP. So I give you a set of cities that you need to travel on. I mean, I need to find the shortest way of doing it. Typical interprogramming formulation, I mean, you have variables that represent whether you travel from city I to city J. You have this constraint if you go out or you go into a city, and well, these are binary variables. And this one type of constraints that you need to add to eliminate structures. And there are many ways of doing this. For instance, typically if you remove one starting node, let's say 1, you have the nodes, the arcs, not considering 1, and the cycles and subset of vertices that also do not consider 1. With this notation, you can define Danzel-Fulkerson-Johnson inequalities to avoid subtours, the empty set formulation, the VL formulation, and the single commodity fold formulation. All of these formulations are a representation of this requirement, no subtours. And you can project this into X variables for all these formulations. I will skip that part. But our main idea in this paper is that, okay, let's consider the empty set formulation, but somehow parameterize this formulation by a constant, dij. Instead of ones, I consider, in a sense, almost arbitrary parameters, but these parameters must be taken to make sense, to be a valid formulation, must be taken in this set, okay? And we obtain a parametric version of the Miller-Tucker-Sedlin formulation. And okay, what are the questions that we study here is, well, first we also characterize the projection onto the X variable space. So because this has additional variables, ui, uj, we compare the formulation for different parameters. So one question is, is the original parameter of the empty set formulation optimal or not? And we also are interested in the closure. So what happens if we use all the formulations for all parameters at the same time? So these are our results. And I can tell you that, for instance, empty set is not necessarily optimal, the original one. Sometimes for different parameters, they are not comparable, and so on. And let me show you the characterization of the adding all constraints. So this is the projection on the X variables. This is comparing formulations. Okay, so sometimes you can compare, sometimes you cannot compare. You cannot compare, and the parameters of the original empty set formulation are not necessarily optimal. Okay. So the closure, so adding all the constraints, you can actually write a formula for this. So the projection onto the X space for adding all these parametric empty set formulation is given by this formula. Okay. So in this last minute, let me tell you that we do this also for the L formulations, for the single commodity fold formulations, and our results, we have results that is similar in flavor. And you can compare all these formulations. So to close this, the DSP is a difficult problem. We don't find a better formulation than the ones known in the literature. But these sort of considered parametric formulations give you like a procedure to find better formulations or different formulations from a different perspective. Okay, just by considering one formulation and parameterize this formulation. And with this, I am done with the talk. Any questions?
So I think in the interest of time, I'm going to open up the breakout rooms, but I just wanted to say thank you everyone for attending and thank you for both speakers. And we have more dots coming in the next season. If you're in the Northern Hemisphere, I guess that's the next in the fall. And stay tuned. So stay tuned. And more announcements from us. We'll see.